So today we've got the, I wanted to definitely review your, what you need to know for your quiz, for your time lab tomorrow, right? Definitely want that to be definitely want to make that as painless as possible for you, right? So the first thing we want to go over is just to reiterate, you've got heaps. The slides for heaps are located in Chapter 6, right? You'll be building a heap, essentially, in the sense that you're going to be writing the code to create a heap, okay? Which isn't that hard at all. The algorithms that you need are on the slide, so there's no reason really that you shouldn't be able to get a full 50% on that one, right? Full 50 points on the heaps. The other two questions, as I mentioned yesterday, the other two questions go on trees, and those are right. I showed you the sum tree on Monday and the equals on Monday. By showing you, I meant I presented the problems to you without giving them a solution, to give you the chance to possibly work on that by yourself. So today what we're going to do is that we are going to work on, I'm introducing a third problem, this number of characters problem, and then I'll go over this problem, and then you guys will work on this problem for like 5 minutes, and then you guys can work on your homework, which is also good practice for the time lab. All right, so both the questions I'll be asking for the quiz, for the time lab will be a traversal style algorithm. Right? There's two types of tree algorithms that you have to deal with. They are zigzag, basically we're trying to find something or find the first empty spot to put something in. A traversal algorithm says, let's go over everything and let's iterate over the entire tree and process everything in the entire tree. Okay? Now, there's one other type, so there's three types of traversal algorithms that we concern ourselves with. There's pre-order, in-order, and post-order. Right? Some problems, the order you do them in doesn't matter. Sometimes the order matters, right? Just really depends on that problem. But the only difference is whether you do you process the root before your children, in between your children, or after your children, right? That's really the only difference. There's one other traversal called level order traversal, which means let's start at the root, and then we're going to go on to the root's children from left to right. Then we're going to go on the root's children's children from left to right, and their children's children from left to right. And that's actually identical to breadth first search, which we learned in Chapter 10. So that one we can just not have to worry about, right? It's a little outlier there. You don't really have to worry about it, but it's useful to know that there is a type of traversal where you can't use recursion. That level order traversal does key. You can't use recursion with that. You have to use a queue instead. So anyway, but what we have are standard traversal algorithms. So let's consider this first problem. Public static int number of characters, string node string root. Now what this one is, and I'll go ahead and I will zoom in just so that's super easy for everybody to read. Okay. So let's go over this one. So the prompt for this would be something along the line: given the root of a tree, okay, or a subtree, I want you to return the number of characters that are in all the strings in this tree. Okay? So here I'm feeding you a tree of strings, right? And I'm not asking for the number of strings. If that was the case, you could just return size and be done with it, right? That would be fairly straightforward, right? I'm asking for the number of characters. So if my tree had only 3 items in it, it had cat, dog, cow, right? All 3-letter animals, then the total number of characters would be 9, right? So, yes?
Wait, are we doing this like now, or did you just do this as an example?
I'm doing this problem, I'm writing up this problem for you. This is not the problem that's going to, the problems that are on the time lab and on the exam and on the final exam are all like this when it comes to trees. If you master this, it's basically 20 points on the final, right? And 20 points on the exam. So it's pretty good. In fact, I think in my opinion, these are easier problems than, in my opinion, the problems that we give on the final are a bit easier for trees are easier than the ones I give on the second exam. And I think that's partly out of choice because there's already so much stuff on the final exam. All right, so how do we solve this, right? So we got to solve this recursively, which means we need to first identify a base case, right? So the question is, what is the base case over here? Well, almost all traversal algorithms start out like this. Because we're always making a local decision. All I'm given is the root of this tree or subtree. So if root equals null, right? So how many characters are in the tree if the root of the tree or subtree is null? 0. Return 0. Boom. That's an easy case right over there. All right. Otherwise, I'm left in this kind of situation, right? I've got some kind of and I bet this is all out. Oh no, it's actually quite. Okay. Otherwise, I'm left in a situation like this where I have a left subtree, sorry, I have a right subtree and a left subtree, right? God knows how many nodes are in there, and then I have myself. So the way I have to solve this is I need to figure out how many characters I have. That's actually very straightforward. Figure out how many characters are in my left subtree, figure out how many characters are in my right subtree, and add it all together, right? Make sense? All right. So let's go ahead and make one variable each to represent that. Int num cars root is equal to int num cars left, or how many characters are in the left side, int num cars right. Okay? And then, so let's figure out, so how many characters would be in the node in the root? Right? That's fairly straightforward. There's one item in the root, right? So that item is root.item. And how would I figure out how many characters are in that string represented by item? Length. Okay. Root.length. Super easy there. Okay, that's fairly straightforward. Now I have to figure out how many characters are in the left string. Yes?
Would there be any reason why you couldn't just call the toString, get rid of the white space, and then use the dot length of that?
Because I might want to include the white space. This is how many characters are in the string. In the string stored in the tree. So we're assuming the processing's already done. Oh, you're talking about...
If you do toString on the tree...
Oh, you're talking about doing it...
And then either keep or get rid of the white space depending on what you want. Okay.
Because then you'll be missing out on a valuable lesson in this case. Okay? Also, you got to be careful when you're doing... You got to know how your processing is being done, right, with that. Right? If you're doing an in-order traversal, like you're using the if you're using the toString method, you got to make sure there's not any additional characters added as well. Right, and if there are, to remove them. So that adds a bit of processing. But we're doing it this way specifically because it's actually a fairly easy and straightforward way to do it. All right, how many characters are in my left subtree? I don't know. That's a hard question to figure out. So we're going to solve it recursively. Right, which means number of characters, what? The number of, that's equal to the number of characters where? Root.left. And that means what over here? Root dot, yep. All right, so I've got, so believe it or not, that's really it. That's giving me the number of characters I stored in the root. This will return the number of characters that are stored in my left subtree, and the number of characters that are stored in my right subtree. Right? Recursion makes things easy for us. All right, so now, what? Now we need to return them. So now, return numcars root plus numcars left. Sorry, numcars left plus numcars right. No. I've created 3 separate variables. Now I'm adding the 3 variables together and returning it. There's no reassignment needed.
But in the above one, when it's saying numchars left and numchars right,
if it keeps going recursively going down the left path.
Why?
Doesn't it just reassign numbers?
These are local variables. These are local to the method. They're local to the method. So in other words, there's no reassignment needing. This method calls copy of num characters left. It only exists inside this method. There's no plus equals needed, right? It's figuring it out, and it's something that many. This is a new variable. Right, and each time you call this method, we create a new variable, right? So each method call is kind of independent of each other one, right? So, I mean, for the sake of argument, let's just see how this works. All right, I'm going to go ahead and let's go ahead and do. Go ahead and do foo, cat, dog, sheep, hello, sheep. All right. So let's go ahead and see how this would process. All right. So we start at the root. Is foo null? No, it is not. So now let's calculate how many characters are in here. There's 3 characters in here, right? So now we calculate how many characters in my left subtree. So let's start at our left subtree. So left subtree says, is this null? No, it is not. So let me calculate how many characters are in here. There's 3 in here, okay? Now let me calculate the size of my left subtree. How many characters are in my left subtree? 0. So we're good. So 0 here. All right. Now it says, okay, calculate my left subtree. Calculate how many characters in my right subtree. My right subtree says, well, there's 3 in this root over here. This left subtree, it's null, so it's 0 characters. Its right subtree is null, so that's 0 characters. So over here, it had 3, 0, and 0. So it passes 3 back to here. So cat says, okay, I had 0 over here, 3 over here, and 3 for myself. So you add those together. So foo's left subtree passes back 6. So it gets 6 back. Now you got 6 here. All right. Foo now calculates the size of its right subtree. Okay. And it says, okay, so the right subtree says, am I null? No, I'm not. Calculate the size of my left. That's 0. So it's 5 plus 0 plus. Well, yeah, and it goes down into this one. It calculates 5 plus 0 plus 0, so I pass back 5. So this it says, okay, I pass back 5 plus 5, and we pass back 6, 10, and 3. We combined that for a grand total of 19. 19 characters. Right? So there's a surprising amount that gets done in just 7 lines. But wait, we can do it in less lines. Right? There's no reason why I can't just do it like this. Well, I can't just, there's no need for those, I don't need those temporary variables. I can just do this. Right? I can just simply do that all in one line. So, solution, including the curly braces, is 4 lines long, albeit one of the lines is a bit long. Okay? All right. So rather than what I did last time, what I did for the morning class, I think I want you guys to take about 5 minutes right now that we've completed this one, to try your hand at sum tree over here. Okay, so try your hand. This is not for credit. This is kind of the idea to see how well you're prepared for tomorrow. Okay, here's the sum tree. It takes in a tree made of integers, not of strings this time, but made of integers, and it says, I'd like you to give me back the sum of all the integers stored in this tree. So, right, if we had 3, 7, and 10, you'd return 20. You would get return 120, right? So it's the same kind of premise here. So do your best to code that up. Shouldn't take you more than 5 minutes, right? Public stacking sum tree gives you back all of the posts. And you don't, and there's nowhere to turn this in. This is just making sure this is more of a self-check for you.
And for some tree, we assume that it's a tree of integers.
Yep, it's tree of integers. So right there. That's why you haven't. That's what the node of integers means. We assume it's a tree of integers. And I actually have to correct the other one. Right.